A warm good afternoon to everyone. Myself, Yalagala Bhavani Prasad, currently working as a Marie Curie ESR Fellow in the BEST Lab, University of Glasgow, under the supervision of Professor Ravinder Dahiya, and my title of the presentation is Silk PVA Composite Based Bioresorbable Nanofibers for Transient Electronic Applications. So basically, for the next 10 minutes, I'm going to first introduce to the transient technology and some of the basics related to the silk fibron, and then preparation for the silk fibron solution, and then typically what is the work we have carried out in the lab, and then what are its structural and morphological characterization with transient studies finally, and some of the conclusions and future work. So basically, what is meant by the transient technology? So transient technology is a type of technology where we fabricate devices on top of a biodegradable substrate, and the materials like electrodes can easily get dissolved, resolved, or physically disappear after certain time. Here in the figure, we can clearly see that the electronic device which is fabricated on top of a biodegradable substrate with biodegradable electrodes and active material completely got dissolved after certain periods of time. So the typical applications are into the electronics, into the bio devices, and into the bio implants, pacemakers, own healings as well. So why exactly we need this transient technology? Our main focus is on reduction of the e-waste. As we know, due to the short life cycle of the electronic devices, the e-waste is generating lot and lot, and these kind of transient technology provides security to the military applications, and it provides eco-friendly and for the helpful of the bio devices like bio-integrated electronic devices like medical devices and neural electrodes, etc. And I want to give a basic introduction to the silk. Basically, silk is a natural ancient biomaterial with lot of advantages like biocompatibility, and its optical transparency is very high. It's very light and bioresorbable, and it's very smooth surface. So because of these numerous advantages, we started exploring the devices fabricated using the silk. And major advantages is its excellent mechanical flexibility, solution processability, and physical property tuning with programmable degradability as well. So this is the typical process flow for the preparation of the silk fibron. Briefly, we'll cut the silk cocoons into pieces and we'll dissolve it in. We'll clean in sodium carbonate 0.02 molar for 30 minutes to remove the sericin which is coated on top of the silk fibron, and later will dissolve in 19:1 ratio of formic acid to CaCl2, and a solution is formed. Later we'll cast it and dry it overnight and thoroughly clean with DI water to remove the calcium which is present inside it, and then we'll dry it overnight, and then we'll prepare the solution according to our desired weight percentage. So next, so when it comes to the work, so here we have prepared a novel material composite using silk PVA composite, which can be explored for different types of applications like nanogenerators, sensors, memristors, etc. And typically, the substrate provides biocompatibility, programmable biodegradability with excellent mechanical and thermal stability, along with solution processability as well. So it's very much cost effective as well. So we want to quickly uh, go to the structural characterizations. So we have performed structural characterizations like XRD, and we have done with the FTIR to calculate the alpha helices, beta sheets, and the percentage of the structural secondary structures which are present inside the silk fibron. And after adding the composite, so what are the structural changes happening inside the silk fibron composite? And for that one, we have performed a Fourier self deconvolution analysis, and we have got the secondary structures like alpha helices, which are 23 percentage, and secondary other secondary structures like 77 percentage of the beta sheets are present inside the composite. And in addition, we have performed Raman spectrum with the to chemically confirm the presence of the silk and PVA. The spectral peaks at 1083 and 1226 confirms the presence of alpha helices and beta turns, and the percentage of clearly calculated using the FST analysis. So here, for a clear understanding of the morphology, we have done the morphological characterizations on the electrospun nanofibers. Here we can see that a very highly uniform and highly porous flexible nanofibers of silk PVA and silk fibron composites have been formed, and the average diameter is for the silk PVA composite varies around 60 to 70 nanometers. So these are very much uniform, and here the optical image has been clearly shown in the figure C. So next we have conducted transient studies on the as prepared composite. Initially the silk fibron prepared using the calcium chloride with the formic acid solution is not at all dissolvable in the GI water, or it's take lot of time to get degraded. After adding PVA composites with different concentrations, we have achieved in succeeding completely dissolvable within the very short span due to the ultra high hydrophobic to hydrophilic conversion of the silk fibron material after the addition of PVA. Here for 1 mg per 1 ml concentration results in 30 seconds, a very quick dissolution rate. And here if we further increase, we are achieving the minimum concentration of uh, minimum within the minimum time of 2 seconds for a concentration of 2 mg per ml, and which can be further explored for different types of applications. And finally, we have successfully prepared a uniform, smooth, highly porous, flexible, and lightweight silk fibron PVA composite. And this can be further used for various electronic applications for the device fabrications as well, like sensors, nano generators, etc. And here we observed that increasing the concentration of PVA results in the increase of the hydrophilic domains inside the silk nanofibers, which leads to the larger number of alpha helices, which is confirmed using the secondary sheet percentage, which is indicated in the table. And later we have performed the water dissolution studies on the silk PVA nanofibers to clearly understand the transient property, as we observe that increasing the concentration of PVA results in the quicker rate of degradation, mainly due to the conversion of hydrophobic domains of silk fibron to the hydrophilic domains of the hydrophobic domains to the hydrophilic domains. So the results show that potential of the presented bioresorbable nanofibers can be explored for various applications like memories, sensors, and optoelectronic devices. Thank you very much. This is our group. Thanks for your coordination. And thank you very much for the funders like Mary Curie ITN and JWNC for the fabrication supports, and EPS Engineering and Physical Sciences Research Council for the funding, and European Origin Mary Curie Fellowship. Thank you.